Good morning to all of you. So today we are going to study digital electronics topic, which is covered under first year syllabus Fundamental of Electronics Engineering. In this lecture, I am going to cover about number system and its representation, then the conversion of number system and binary arithmetic, that is addition and subtraction, and lastly we will cover about the subtraction using complements. First of all, what is digital electronics? Digital electronics is basically a field of electronics which includes the study of ones and zeros, that is digital signals. And why we use digital electronics? Because in the era of digital, it is easier to understand the on-off, that is two logic system, which is digital, and it is easier to design equipments having only two logics rather than analog electronics. So, digital electronics are usually made from large assemblies of logic gates, and complex devices may have simple electronic representation using Boolean logic function. Now, the very first thing which comes into our mind starting digital electronics is number system. What is digital? So, before starting digital, what is a number system? A number system is basically a system of writing numbers. Since our childhood, we have studied decimal number system, that is number consisting from 0 to 9, that is 10 numbers. We are quite familiar with this number system, which is a decimal number system, and the total number of digits which occurs in this number system is 10, which is also called as base of this number system. So, a number system is basically a mathematical notation for representing numbers of a given set by using digits or symbols. Each number has a unique representation and arithmetic and algebraic structure of certain figures. In a number system, it allows the operation, that is addition, subtraction, multiplication as well as division. In this syllabus, we will study 4 basic number system which comes into our use. The 4 basic number systems are decimal, binary, octal and hexadecimal, which are classified based on the number of digits exist in that particular number system. For example, in decimal, the total number of digits exist are 10, that is 0 to 9, and hence the base is 10. In binary number system, which is basically an on-off number system, only 2 digits exist, that is 0 and 1, or we can say the base of this number system is 2. In octal number system, base is 8 and the digits exist are from 0 to 7, and in hexadecimal number system, the base is 60. The digits exist are from 0 to 15. Basically, it is 0 to 9, then 10 is represented by A, 11B, 12C, 13D, 14E and 15 is called as F. So, these are the 4 basic number systems which are most widely used in today's era of digital electronics. Starting from the very first, that is decimal number system. This number system has base 10 and the 10 existing digits are from 0 to 9. This means any numerical quantity can be represented using these 10 digits. Decimal number system is also called as a positional value system. This means that the value of digits will depend upon its position. The position is aligned with starting from the rightmost digit with lowest weight, that is 10 to the power 0, then next digit is having weight 10 to the power 1, next digit is having weight 10 to the power 2 and so on. So, it is also called as weighted number system, and the weight of least significant digit is 10 to the power 0, whereas the weight of most significant digit is highest weight. In this example, I have taken 10 to the power 2. So, if we consider a number say 734, then the weight of 4 is 10 to the power 0, weight of 3 is 10 to the power 1, whereas weight of 7 is 10 to the power 2. Or we can say that the value of 7th position is 7 into 10 to the power 2, that is 700. In the next number 971, the weight of 1 is 10 to the power 0 and 7 is 10 to the power 1. So, the value is 7 into 10, that is 70. Whereas in 207, the weight of 7 is 10 to the power 0, or we can simply say that the value of 7 is 7 units, or simply 7. So, the value of any number is dependent on its position, starting from the rightmost digit having minimum positional weight of 10 to the power 0 to leftmost digit having most significant weight of 10 to the power n minus 1. So, the weight of each position is expressed in 10 to the power n, and any instruction in analog electronics is given in the form of voltage signal with 10 different voltages. It is quite difficult to implement such a system in digital equipment, so we move towards binary number system. It is basically the easiest way to vary instructions because it is just a two-state system, that is on and off. On is represented by 1 and off is represented by 0. And hence the base of this number system is each binary digit in binary number system is also called as bit, with minimum weight 2 to the power 0 and with rightmost digit and the leftmost digit has maximum weight, also called as most significant bit, and the rightmost is called as least significant bit with minimum weight. So, for example, if the given number is 11010, then the least significant bit is 0 and its weight is 2 to the power 0, whereas most significant bit is 1 and its weight is 2 to the power 4. Next weight is 2 to the power 3, 2 to the power 2, 2 to the power 1 and 2 to the power 0. Now, any decimal equivalent, any number can be easily converted to its decimal equivalent value by the weighted sum, that is the value multiplied by weight. So, if we have to convert this binary number to decimal equivalent number, then it is 1 into 2 to the power 4 plus 1 into 2 to the power 3 plus 1 in 0 into 2 to the power 2 plus 1 into 2 to the power 1 plus 0 into 2 to the power 0, which comes out 16 plus 8 plus 2, that is 26. So, this is its equivalent value in decimal number system. So, computer memory is also measured in the number of bits it can store, and the smallest unit of binary is bit, and the next higher units are byte. A group of 8 bit is called as 1 byte. Then 1 kilobyte, that is 2 to the power 10 bytes, 2 to the power 10 which is 1024. Then 2 to the power 10 kilobyte is 1 megabyte, and 2 to the power 10 gigabyte is 2 to the power 10 megabyte is 1 gigabyte. Now, moving towards another number system, that is octal number system. This number system has base 8, that is the numbers ranging from 0 to. Octal number system is also a positional number system with least significant digit having weight 8 to the power 0, and the most significant bit is the leftmost bit having highest weight. For example, if this is the given octal number, then we can easily find out its decimal equivalent by weighted sum method, that is 8 into 8 to the power 0. The weight of these digits is 8 to the power 0, 8 to the power 1, 8 to the power 2 and 8 to the power 3. So, 7 into 8 to the power 7 multiplied by 8 to the power 3 plus 2 multiplied by 8 to the power 1, 8 to the power 2 plus 6 multiplied by 8 plus 8 multiplied by 8 to the power 0 is the resultant number, which comes out to be 448. No, this is wrong. Multiplied by 8 plus 8 multiplied by 16 plus 48 plus 1, and we can simply sum up this number to find out the decimal equivalent number. Another number is hexadecimal number system with base 16 and the digits exist are from 0 to 15, which are further divided from 0 to 9, then A, B, C, D, E, F. So, 0 to 9 and A to F are 16 symbols which exist in hexadecimal number system, where A is equivalent to 10, B to 11, similarly 15 is equivalent to F. It is also a positional number system with rightmost digit having minimum weight 16 to the power 0, and this weight continues to increase towards left. And we can easily convert any hexadecimal number to decimal equivalent number by again weighted sum. For example, the given number is 27FB. So, weight of B is 16 to the power 0, F is 16 to the power 1, 7 is 16 to the power 2 and 2 is 16 to the power 3. So, 2 into 16 to the power 3, 7 into 16 to the power 2, 15 into 16 to the power 1 and B, that is 11 into 16 to the power 0. So, the resultant number comes out to be. Why we have studied octal and hexadecimal number systems? Because in a binary number system, if we have to represent all the digits, then it becomes quite a very large size number. So, to reduce the size and to save the memory, we divide or we increase the weight of number system, and that is why we use octal and hexadecimal. Later on we will see how to convert octal to binary and hexadecimal to binary and vice versa. Now, starting from the very first conversion, that is converting decimal to any binary number, to any other number. First of all, we will generalize the procedure. If we have to convert any decimal number to other number system, for integer part, use successive division method. That is, divide the integer part by base of the required number and retain the remainder in reverse order. That is, perform successive division by 2 if we have to convert it to binary. Place the remainder from right to left, that is in reverse order. For example, if we have to convert 42 to base 2, we will divide 42 by 2 and place the remainder here. Then 2 and 20, the remainder is 1. 2 5s are 10, remainder is 0. So, 2 is 4, remainder is 1. 2 1s are 2, remainder is 0. So, we will write this in the reverse order, that is 1 0 1 0 1 0. So, the resultant number will be 1 0 1 0 1 0 binary. We can also use another way, like to express 42 as a multiple of 2's, that is, it can also be written as 32 plus 8 plus 2. So, the weight of 2, that is 2 to the power 1, 2 to the power 3 and 2 to the power 5. So, we write the weights as 2 to the power 0, 1, 2, 3, 4, 5. put 1 2 to the power 5 in front of 2 to the power 5, 2 to the power 3, 1, 2 to the power 1, 1 and all remaining are 0. So, this is also another method to convert decimal to binary. We can use any number, any method to convert a decimal to binary number. We have already discussed about this method. Like if we have to convert 45, we can write it as 32 plus 8 plus 4 plus 1, that is 2 to the power 5, 2 to the power 3, 2 to the power 2 and 2 to the power 0. Sorry. So, we will write 1, 0, 1, 1, 0, 1. Or we can simply convert this number by division, successive division. 45, 2 2 is 4, 4 and the remainder is 1. Then 2 1 is 2, remainder is 0. 5 is 10, remainder is 1. 2 2 is 4, remainder is 1. 2 1 is 2, remainder is 0. And we write it in the reverse order, that is 1 0 1 1 0 1. That is the same number. So, we can use either of these two methods to convert any decimal to binary. Similarly, we can also convert 25 divided by 2 using successive division. 25 divided by 2, that is 12, remainder is 1. 12 divided by 2, that is 6, remainder is 0. 6 divided by 2, that is 3, remainder 0. 3 2 1 and we write 1 1 0 0 1. Simple way to convert any decimal to binary number. It is the easiest way to convert any decimal to binary number, that is successively divided by 2 and record the quotient and remainder in reverse order. These are certain more examples, and if there is a fractional number, then we have to follow separate routine for integer and for fraction part. Like for integer part, we will do successive division, that is 12 divided by 2, that is 6, remainder is 0. Then 6 divided by 2, that is 3, remainder is 0. 3 divided by 2, 1 and remainder is 1. So, the integer part is 1 1 0 0 point. Now, moving towards the fractional part. For fractional part, we multiply the number with required base and retain the integer part in same order, like 0.0625 multiplied by 2, which comes out to be 0.125. We retain the integer part and further multiply it by 2. 0.125 multiplied by it 2, that is 0.25. Again we retain the integer part and further multiply 0.25 multiplied by 2, that is 0.5. Again preserve integer and 0.5 multiplied by 2, that is 1.0. Once the fraction part becomes 0, we stop, and if there is a case that the fraction part continues, then we will go for 4 to 5 steps and then we stop. And then we use the write the integer part in same order. So, the answer will be 0.0001. I hope this method is quite clear to all of you. Now, decimal to octal conversion. We again use the same method, but instead of 2, we divide the number by 8. So, we have to divide 315 by 8. 8 3 is 24 and 7 and 5, 8 9 is 72. So, remainder is 3. 8 4 is 32, remainder is 7 and this one is remainder. So, the number is 473 base. So, this is the way to convert decimal to octal. Similarly, we can convert any decimal to octal number by using repeated division method, divide the integer part by 8 and retain the remainder in reverse order. If there is a fraction part, then again we use the same method, that is multiply the fraction part by 8 and retain the integer in same order. Now if we have to convert 359 decimal to octal, simply divide 359 by 8. 8 4 is 32, 3 or 9, 4 is 32, remainder is 7. 8 5s are 40, remainder is 4. So the answer is 5 4 7 base 8. Hope this procedure is quite easy. Similarly, we can also convert 427 to octal equivalent. Simply divide 427 by 8. 8 5s are 40, 2 7, that is 8, 3 are 24, and the remainder is 3. Then 8 5 is 40, 8 6 is 48, and remainder is 5. So the resultant is 653 base 8. Now moving towards fraction part, we use same technique, that is multiply the fraction part by 8 and retain the integer part and further divide the fraction part until decimal part becomes 0, or we will move to 4 to 5 steps and then we stop. So for integer part we divided by 8, 225 divided by 8, the remainder is 8 2 is 16, 6 and 5, 8 8 is 64, 1 is the remainder, then again 8 3 is 24, 4 is the remainder, then 0, so it is 341. Now for fraction part, 0.25 multiplied by 8, that is 1.8, we retain the integer part, then 0.8 multiplied by 8, we retain the integer part, then 0.4 multiplied by 8, that is 3.2, we retain the integer part, then 0.2 multiplied by 8, that is 1.6, again we retain the integer part, then 0.6 multiplied by 8, again we retain the integer part. And as we see that the integer part will not close to 0, so we move up to 4 to 5 steps and then we stop, that is the answer will be 1 6 3 1 4. So 341.16314. From octal now we move towards hexadecimal. How to convert any decimal number to hexadecimal? We use same procedure, that is divide the number by 16 and follow same routine, that is retain the remainder in reverse order. So 315 divided by 16, that is 19, and remainder is 11, which is written as B. Then 19 divided by 16, quotient is 1, remainder is 3. So we write 1 3 B. Another number, that is 830 to hexadecimal. So 830 divided by 16, that is 16 5 is 80, 16 1 is 16, remainder is 14, that is 14 is called as E. Again 16 3 is 48 and remainder is 3. So the answer is 3 3 E. We take one more example of decimal and we use same routine, that is first 225, integer part divided by 16, 16 divided by 225 divided by 16, that is 14, and remainder is 1. Then 14, so answer will be E1. Now so our second part, 0.225 multiplied by 16. So 0.225 multiplied by 16, which comes out to be 3.6, retain the remainder. Then 0.6 multiplied by 16, that comes out to be 9.6, retain the remainder. And again we say that 0.6 continues, so we stop. and write it as 3, 9. As 9 is repeated, we can also insert a bar over 9. Now converting from binary to decimal. For this, we use the weighted sum approach, that is, write the weights. Weight multiplied by value is its decimal equivalent value for any number system. That is called as weighted sum method. For example, if the given number is this, then its weight is 2 to the power 0, 1, 2, 3, 4, 5, 6. So the value will be 2 to the power 6 plus 2 to the power 3 plus 2 to the power 2 plus 2 to the power 0. 2 to the power 6 is 64 plus 8 plus 4 plus 1, that is 77. So this is the simple way to convert any number to decimal. We use weighted sum method. It is also called as multiplication algorithm. Multiply each value by its corresponding weight and sum up all the values to find out the decimal equivalent number. So for example, if the number is 10101101, then weights are 2 to the power 7, 2 to the power 0, 1, 2, 3, 4, 5, 6 and 7. So the resultant number will be 2 to the power 7 plus 2 to the power 5 plus 2 to the power 3 plus 2 to the power 2 plus 2 to the power 0, which comes out to be 128 plus 32 plus 8 plus 4 plus 1, that is 173. So we can easily convert any number to its decimal equivalent. For example, for this number we write the weights. So its number will be 2 to the power 4 plus 2 to the power 3 plus 2 to the power 2 plus 2 to the power 0, that is 16 plus 8 plus 4 plus 1, that is 29 to the base 10. I will leave the rest 2 questions for all of you. You can easily convert these by converting it to the weights. The weights are written as it is. It was 0, 1, 2, 3, 4, 5, 6. Or we can say 2 to the power 6 plus 2 to the power 4 plus 2 to the power 2 plus 2 to the power 0. For next number, the weight are 2 to the power 0, 1, 2, 3, 4, 5. So the number will be 2 to the power 5 plus 2 to the power 2 plus 2 to the power 1 plus 2 to the power 0. So hope all of you can easily convert it. 2 to the power 6, that is 64 plus 16 plus 4 plus 1, and for this it is 32 plus 4 plus 2 plus 1. So any number can be easily converted to decimal. And for this decimal to binary, we have already seen that we divided the number system by 2. I will do only one and then leave the rest for you all to practice. So 2 2 is 4, 1 and 9, 2 9 is 18, remainder is 1. 2 1 is 2, 2 4 is 8, remainder is 1. 2 7 is 14, remainder 0. 2 3 is 6, remainder is 1. 2 1 is 2, remainder is 1. So the number is 1 1 1 0 1 1. This is 2. Similarly, we can easily convert binary to octal number by grouping the number in a group of 3. Like if the number is written as a this, then we try to group it from the extreme left side, and if there is a need, we add an extra 0, and 101, that is 5, 011, that is 3, 110, that is 6, 010, that is 2. So it is 2635 octal number. And if we have to convert a binary to hexadecimal, then we group in a form of 4 digits. For example, if this is the digit, then we group it into 4, 0 1 0 1 that is 5 and 1 0 1 1 that is 11 which is written as B. So, the resultant number will be B5. I will leave the 2 exercises for all of you to convert these binary number to hexadecimal, and we will stop right here and we will continue to the conversion and binary addition and subtraction in next lectures. Thank you all.